Hi and welcome to this video about process hollowing, or really some kind of process hollowing. It's not exactly the classic hollowing, but it is, well, sort of. At least it should be interesting. So process hollowing is a fairly well-known technique where you create a process in suspended state and then somehow unmap the existing executable within the process address space and then map your own executable or some other code into that process address space and let it start running. And so from the outside it might seem like a benign process like Explorer or SVC host, but internally it's actually a completely different thing that is really running. So I want to show you one kind of interesting example of doing something like that. It's not perfect probably, and I haven't tested that in all scenarios, but something to look into perhaps, or just showing a few ideas. So what is process hollowing that I'm going to try to demonstrate here? So we'll start with an attacker process. This process will try to hollow another process. It will do so by creating the process in a suspended state. That is, the main thread has not yet started execution. At that point, there's not much within the process except the executable being mapped and anti-DLL. And so classic hollowing tries to remove the existing executable within the address space, and I say, why remove it? Maybe it's better to leave it there because then it's less conspicuous when you try to add something else into the process address space. So we'll leave it there, but we'll map a malicious executable, a different executable if you will, into that process address space, and then make sure that it's being called by the main thread. So essentially the original image is just laying there dormant while our replacement image is the one executing. The final step we'll have to do in order for that to properly work is to point to the PB. There's an image base there. We'll have to point that to our replacement image, otherwise anti-DLL, the loader, is going to be confused. And the final step is very simple. Just resume the main thread and we're done. At that point we can remove the attacker, it can go away, and we have something else running within that process. Okay, let's see what we can do about that. So I created already a new project just to save some time. This is going to be our attacker. I'm going to call it hollowish because it's kind of a hollow thing, but not really a true process hollowing. So let's begin. First, we need to have two parameters here. We need to have the executable to run as the outer shell and another executable to use as the replacement. So let's just do some checking here. If we don't have enough parameters, let's use a printf saying that the usage is hollowish, and then we have sort of original and if I can spell, and replacement. Something like this. This keyboard is a bit annoying. And return 0, and we'll add include for stdio. So once we have these executables, we can start by creating the process for the original executable in a suspended state. So for that we have to create a process. So we have this process information stuff and startup info. And we're going to create the process in a normal kind of way. So we'll have the call to create process, as we typically do in many of these cases. I'm going to remove the const here so we can properly compile create process W. So we have null pointer here. Here's argv1. That's going to be the path of the executable we would like to create. We don't need any special settings here. We just need to kind of move forward. And the only thing we do need to do is to use the create suspended flag to create the process in suspended state, so the thread is not actually executing that code. So now we have some default parameters. Let's just deal with them. And finally we have these SI and PI to provide to the call. SI is input, which in this case we're just setting up the size properly, and PI is going to give us the result of the call. So if that doesn't work for some reason, we'll just return 1 as an error, and that's it. I'm not going to even bother writing any message. We'll see if something doesn't work as expected. We'll try to figure it out using a debugger. So now we have the process created. This should be a benign process like Explorer, for example, something simple that is not going to be suspicious on a typical system. So the next thing we want to do is to open a handle to the file we'd like to map into this new process. So that's our replacement executable. So I'm going to use the normal create file function to open a handle to that file. So we have the file name, which is coming from the command line, argv2 that's going to be. And then we want to just read stuff from there. There's no need to make any changes here, at least not for now. We can have a sharing for read. If anybody else wants to read the file, that's fine too. We can live with that. And then we have a null pointer in terms of there's no need for any kind of special security because we're opening an existing file. So we have open existing here. And then we have some flags we don't care about and a template file which we don't care about either. So we're trying to open a handle to the file. And again, this could fail in various ways. Maybe the file is just bad path or something. So invalid handle value is what we're going to get. So if we get that, something went wrong, let's just bail out and we're done. So now comes the more interesting part. How do we actually use this file? We open the handle, great. What's next? Well, we want to allocate memory in the target process where we'd like to map this file. So we need to find some free space for that. So I'm going to go ahead and use the function. Let's call this the address here we're going to get back. Let's call that new address. I'm going to call virtual alloc.ex. Which alloc.ex is the one that can allocate memory in a different process. We have our handle to the process we just created. And remember, when we create a process, the returned handle has the process all access mask, which means that we can do whatever we want with the given process. So it's not a problem allocating memory in that new process. The address, we don't care. In fact, we want to get some address which is available. The tricky part perhaps is the size. What is the size that we should allocate? And it has to do something with the file size that we're actually trying to map in there. So I can definitely use get file size to get the file size, but that might not be good enough because if you're familiar with the portable executable format or PE, when it's actually mapped into memory, it's not going to take exactly the same size as it is on disk. And that's because all mappings have to happen in granularity of 4K of a page, and each page might have different protection, so they can't really overlap in certain cases. And that's why you can see things like headers are always separate than the actual code or things like that, other sections. So that we can't just have exactly that size, we need some more. And how much more is actually difficult to determine. We can just give it a shot, and it doesn't really matter because it's not that much more. Maybe 1 megabyte here, I'm going to have another 1 megabyte, even 2 megabytes. It's really not that bad. Either way, it's not going to be like very noticeable, because we're going to allocate the size of a file, which could be big, could be small. It really depends, and if we know what we're going to inject, and of course we know the size of the file, so we can better adjust that extra perhaps. But I'm going to stick with something simple like 2 megabytes. This is 2, shifting 20 positions bits to the left, that's multiplying by 2 to the 20th power, which is mega. So we have 2 mega here as an example. And of course, we need to be able to perform the allocation fully. So we have to commit and reserve. This is basically saying I'd like that memory to be available to me. And then comes the protection. So the protection here is kind of tricky. What should the protection be? And the thing is that sections in a PE, each one requires their own protection. It could be different. For example, data is typically protected with read-write. Read-only data is protected with read-only, just like a header. And code is protected with execute-read. So technically speaking, the best way to go about it is to choose some initial protection, but then change the protection appropriately based on the sections that we're mapping. But here I'm going to be lazy and say, let's just go ahead and use a read, write, execute. Just have everything, every possible access, so we don't have to worry about that. Now, obviously, this is not ideal because some anti-malware tools might notice that you're creating or allocating memory with execute read write, which is all possible permissions. But in this case, again, I'm going to save some time, and this is a nice opportunity for you, dear viewer, to customize that if you see fit. So if that doesn't work out, it means we're really like completely out of memory, which is going to be really bad. So really nothing to do, just bail out, we can move on. So now we have an appropriate memory that is allocated in the target process. So what do we do next? What we want to do is to take the executable that we want to map and map it into this address called new address. However, the problem is that when you take an executable, it is built so that it can be mapped into a certain address, its preferred address. And it's unlikely its preferred address is going to be the one that we allocated here. In fact, the chances are very, very slim. So what we need to do is to rebase the executable to be compatible with this new address. This is one way of doing it. This is not the typical way hollowing works. What typically does happen in hollowing, in classic hollowing, is that the mapping is done here manually. So all the required fix-ups and so on is done here manually, which is it is a chore. You can find examples of how to do that online on GitHub, but I'm going to take the easy way out, so to speak, and I'm going to have an API do that for me, and essentially changing the binary itself, the executable itself, to be compatible with that address in memory. So I'm going to have a function here called rebase image 64, which is available in something called image help, which is an API that Microsoft provides. So we're going to call this function rebase image 64. That's the one we want to use. That's the kind of full function, so to speak. I think there's a W version. If not, we'll have to do something about that. Apparently there isn't. So we need the current image name, and the current image name is the one that we want to change, that argv2. But now we're kind of a little trouble here because we have a Unicode string here. We need now an ASCII string, which is a bit annoying. So let's just change everything here, and instead of using wmain, which I should have used here, let's just use a normal main and use a normal character, that is a ASCII character. And we just make the changes. We use create process A just to be lazy, and create file A to take the ASCII version. It should be fine, not really a very big deal. At least definitely not for this kind of experimentation. And now we can use argv2 here as a parameter. That's our replacement executable. And then we have the symbol path. We don't have any symbols planned, so we're not going to depend on any of that. We do want to perform the rebase, so otherwise just kind of making us making some preparation, so to speak. And this is not a system file, and we don't want to rebase system files. We don't want to touch them. We just want our particular executable. Going down, there's no need to do that. And check image size. Well, there are some defaults there which we don't really need to deal with. 0 is fine here. And then we get the old image size, so kind of a thing that maybe might be useful later on for planning. But let's just go ahead and create some variables to capture some of the information here. So some things we're just getting back, and we kind of have to take it whether we like it or not. So we have the old image size. So let's call that, let's call that old size to make it more compatible with the naming here. And then we have old image, the old image address here really. And so we need to get that as well. So that's going to be ulong64. That's all old image base. That's the old image base. And we also have the new image base that we're going to get back. And this is supposed to be, of course, ulong64, the new address. So essentially we are saying we'd like to map into this new address. So give me the old address. If I need that, I'm going to use that. Otherwise, I don't really care. So we have the old image base here. That's the original image base that the PE wanted to be mapped into, which we don't really want because it does not align well with what we want. We want the new address to be used. And now we can specify the new size. It's going to give us the new size back, which is basically what I was trying to kind of calculate here in not a very precise way. So technically you could call that without doing the rebase, get the new size, then allocate appropriately and so on. So I'll leave that to use an exercise as well. And then we have the new address. That's the new image base that we like to use. So it's a parameter there that is going to be used as is and hopefully returned appropriately. And that's it. Let's see if that doesn't work for whatever reason. Again, not going to bother with any kind of error handling. So now we're done. So the executable is actually changed in place, which means that if it's signed, its signature is going to be invalidated, but hopefully we're talking about something we'd like to inject here. So that's probably not something that is properly signed or anything like that. We just want to stash it into the process, the benign process or the innocent process without it being detected, for example, here. So what should we do next? We need to copy information, or at least to write into the target process the information coming from the file. Now that the file has been properly rebased, we need to copy information from the file, in the sense that we have to copy all the sections of the PE, the header, things like that, to make it a true PE, so that NTDLL can think that this is just the original PE and can just use it normally. So this requires us to do some work. The first thing I'm going to do, I'm going to map the file into memory to make it easier to do copying. Otherwise, I would have to create buffers and map them and all that. It's kind of annoying. So we'll use create file mapping here to take our file and map it into create a memory file object for that, and then use map view of file to actually map it into the address that we want. And so create file mapping first, and if you're not familiar with create file mapping and all that, I did a bunch of videos about file mapping a few years back, so feel free to browse older videos. I'm demonstrating there how to do shared memory with file mapping. So we have create file mapping. Let's call that. The second parameter is security, which we don't care about. The protection is going to be read only, because we just need to read information from the file. We don't need to write anything new. That's already been done by the rebasing. And with the size, we can just specify 0, indicating we'd like to map or to open something that maps the entire file. So if that doesn't work for whatever reason, again, we'll just bail out. This is likely to work. And now we can actually perform the mapping. Technically, we can also close the handle to the file. We don't need it anymore because we already mapped it, and internally the file mapping object is going to hold on to another reference to the file. So technically we don't need the handle, but this is just me being picky here. So next we need to get the mapping, and to actually make the mapping into the address space of our process. And I need to use the map view file or file ex function here, because it allows me to ask for a particular address, which I know is available because we made sure of that. We made sure that there's memory there, that we know that this address is exactly the one that we need. So we have hmap here. The desired access is file map read. You just need to read this thing. And then we have from the beginning of the file all the way to the end, and the address that I want is new address. So technically the address returned here is supposed to be the same as new address technically. But we don't need to kind of know that. Of course, if this doesn't work, then something went wrong and we can just bail out again. So assuming everything is fine, we can now start doing the copying. So we have to copy the header, we have to copy the sections, and this will require us to do some manual work. It's not like automatic kind of thing. This is typically something that loader might be able to do more easily, but that's where we are. So we have mapping in the address there. So the first thing I want to do is to parse the PE. We'll have to parse some aspects of the PE. It's not that fun perhaps, but it's not too bad either. So we have first the DOS header. If you're familiar with the PE, it starts with the DOS header. So we can use p image DOS header as the pointer here to do the casting. And in fact, there are some helper functions we can find, like get image anti-header, things like that, which are in fact available, so it's not that bad. But I'm going to use maybe something as pure as I can to make it maybe easier to understand. So we're going to look at the DOS header there, and then need to find the actual anti-header. So anti-header is the specific one for Windows these days. So we have a structure called image anti-headers, which we need to grab, and it is provided by the address. Of course, we have to cast that to be pointed to a byte, so the calculation of is done using bytes and not chunks of image DOS header. And so if you're familiar with the PE, again, there's this member called e_lf new, which is the offset to the beginning of the anti-header. So just doing that and some casting to make the compiler happy. And then we can look at where the sections begin. And the sections begin exactly after the header. So technically the structure there is called image section header. Technically these are the headers and they are followed by the actual sections. I'm going to use anti-header +1 here. So this seems a bit weird perhaps, but just notice that when you add to pointers in C and C++, it's not adding bytes, it's adding the number you provide times the size of whatever that thing is pointing to. Since anti-header is pointing to image anti-headers, it actually adds size of image anti-headers bytes. That's exactly what I want, because this is where the headers begin of the sections. So now we can start doing the actual work of copying information from the original file into our target process. We don't want to depend on the file for later on. And so we need to start with write process memory here. We need to write to the process. So remember, we have the all-powerful handle to the process, so there's no issue in that respect. The address, of course, is the new address. This is where we'd like to write our new data. That's where we begin our PE within the target process. So that's the base address. The buffer we want is the first thing we really need here is the header. So we have anti-header, and there's something here called optional header, and we have the image base. So basically we want to copy information from the image base. The image base is where the initial PE really should start in memory. So what we have here, the first parameter here is the base address that we'd like to write to, and this is where we find the buffer. So the buffer is part of the memory we've just mapped, and starting with image base. Because of the rebasing, that should be the correct address there. And then we have the size. So the size is supposed to be the size of all these headers. And although we can go with a simple, just take 4K as one page, we're going to be more precise than that, because the optional header has a size of headers member we can actually take advantage of. So we can just do that. And then the last parameter returns how many bytes were actually written, which we don't care about. It's going to be the same one if everything goes as planned. So that's kind of the header. So the header is sort of fine. Now we need to copy all the sections. So that's something that will require us to have a loop. So we have a loop. We can see in the anti-header how many sections we actually have. So that's actually in something called a file header. There's a number of sections here. So we're going to loop over all these sections. And for each section, we'd like to write process memory into our target process, the contents of that section. So the handle is easy. The base address is supposed to be calculated by taking new address and adding to that the section virtual address, which means basically the offset of the section where it actually is starting. So we have sections there, and that's the header. So for section at index 0, it should be written into virtual address. So it's important to know that this is not the virtual address really, it's actually an offset. It's called the relative virtual address, or RVA in P parlance. It's actually the offset from the beginning of the image. So we have the beginning of the image in new address, and we have to add to that in order to get to the appropriate section here. So that's going to be our address to write into. So the compiler is not happy simply because new address is pointer to void, and that's not going to work out. We can't add pointer to void. So I'm just going to cast that to pointer to byte for the compiler to be happy. Then we have the buffer, which is the source where we're going to read data from. So we have sections I, and sections I has this pointer to raw data. This is where the section data actually starts. And of course, we have to add to that the image base, because that's really where the image is being mapped into memory. So this is where we expect to find this information. That's the actual buffer. So it's actually, maybe it's better to write that in the opposite direction, so in reverse. So we have the image base, and we add to that the pointer to the raw data. The only thing left to do here is to make the compiler happy, because both of these are just numbers, and the write process memory requires a pointer here. So we can just cast that in this way and say, okay, fine. And the size, of course, is supposed to be brought to us by the sections as well. So under sections, there's a size of raw data. That's the actual data, the size of that particular section. This is where you might want to add the check for the type of section, and based on the type of section, you might want to change the page protection. So as I've shown already, I've just mapped everything with page execute read write just because I'm lazy, but you can add that to be more precise without having that execute read write everywhere. So how would you know? Well, the sections every section header has a bunch of flags, and the flags indicate the protection of that section. And so as a simple example, if I just open some executable in Total PE, which is one of my PE viewers, one of my tools, but you can look in any PE viewer of sorts, you'll find that in the sections area, you can see here the characteristics. These are the flags indicating what kind of protection is required there. So you can definitely go ahead and do whatever you need to do to make that work correctly. So you might need to actually do some tweaks here, because some parts might be with copy on write. You might want to have that flag as well. So here I'm kind of cheating a little bit and not doing the full work, because I'm trying to just demonstrate an idea, and it's not like a bulletproof kind of thing, but something you can get started with to maybe try doing things your own way. So now that we've done that in a loop, we've copied all the sections, which is basically all the stuff that we have in the executable really. So the only thing left to do here is to make the NTDLL, the loader, happy well, actually two things we'll have to do. One of them is to change the PB. PB is the process environment block. It's a process-wide data structure and user space that has some information about the process, and it has to point to the correct image base. And by default, it points to the image base. It will point to the image base that, of course, we have in the original executable, but we want it to point to our image base, the one that we used as a replacement. And otherwise, it's not going to work out well. NTDLL is going to crash. And so for that, we have to get to the PB itself, which is something that we can do if we need to do that. In fact, we do. So here's the way to do that. We need to call the function anti-query information process. This is one of those undocumented APIs from native API. It is partially provided in the documentation in a file called winternal.h. So I'm going to take advantage of that. If I go to anti-query information process, there's also a few information classes that are provided here that we can perhaps use, like one that we need, which is process basic information. You can see it is provided here in some way. So that's going to actually be good enough for us. Let's give it a shot. So first we need a structure here, which is process basic information. Let's call that BI, and then we can call anti-query process information process, providing the header, which we have, of course. The information class is process basic information, and that's because in that structure called process underscore basic information, the image base is supposed to be here. So sorry, the PB address is supposed to be here. Indeed, it is right here. And even though most of the structure here is not provided for us, it's all like reserved kind of stuff, still it's good enough. We just need the PB address so we can get it from there. So we have the structure BI here and size of BI. By the way, if you do want to have all the information about these native APIs, you can look at the PHNT project on GitHub that has most of the Windows native APIs, including full declaration of the structures. And in fact, I've written a book about that, Windows native API programming, that leverages many of these APIs. So the PB here, obviously, is something we can now get from the process basic information, the PB base address, that's the one. So although we get here the pointer to that, we can look at the structure, see what we get. You can see the structure also is a big one, but not really provided with any documentation. So unfortunately, we do have to go a bit beyond here and look for the structure within the PHNT headers to see exactly what that looks like, or use the symbols in any debugger to see where the image base is. So I can always already kind of tell you that the image base is 16 bytes from the beginning. So it's somewhere here in one of these p voids, in fact. And so I won't show you the full declaration of PB. You can just go ahead and find it online or in the symbols or in the PHNT headers. It's there, it's available. And so I just know that this is where the full image base is. This is where it's supposed to be written to. So now we can go ahead and write it. So we have write process memory again. We're writing to our target process. The base address is going to be that PB. So we need to take P byte here. We're going to take the PB address that we got, and I'm going to move 16 bytes forward. So that's times 2 times size of any kind of pointer, or just use 16. But for 32-bit, you need to move a different amount, probably only 8 bytes. So you have to be kind of careful here. But I'm going to use just 64-bit processes here for this demonstration. What we want to actually copy into there is the image base. So we need to go to the image base. So we have that in the NT headers. Let's just use the next line to make it easier to see. NT headers has that optional header, and image base is here. So we need to write this data. This is as a number. So we need to take the address of that, and the size of that, of course, is the size of any pointer, really, because it's just an address in a 64-bit process. So you can write that, and we're done with that. The really last thing, well, almost the last thing we need to do is to tell NTDLL, based on its expectations, where the entry point is of the executable. The entry point is also part of the header, so we have to put that into a register, into the RCX register, in fact. And to do that, we have to get the set of registers the thread is using. That's the first thread in the process that is currently in the suspended state. We have to get its context. So context is a platform dependent or CPU dependent structure, and we can get that information for the thread and change RCX, which is going to be used by NTDLL later once it's done with the usual initialization. We just need to specify what kind of registers we'd like to get back. We don't need everything, so we can get away with context integer, meaning I just need the normal, the simplest registers like REX, RBX, RCX, and so on. So I need to get them by calling the getThreadContext function. This is the function you can call to get the state of every thread, but you have to be careful only calling that when the thread is in a suspended state. Because if it's not in a suspended state, once you call that, it's kind of silly because it's already changed. So you have to put the thread in suspended state first. In this case, of course, we know this is the case. That's how we created the process where the first thread is suspended. So we have the handle to the thread. We can use that and get back the context. I'm not going to do any error handling here. I'm going to assume it's going to work out, and just need to change RCX here to the actual entry point. So how do we do that? So we have the new address, which is our base address, that is where the new executable is being mapped into that benign executable. We just need to find the offset there. So it's possible to get that from the headers. From the headers, we have optional header, which by the way is not really optional. The name is kind of misleading. For executables, it's always mandatory. And then we have address of entry point. This is what we want. We need the address of the entry point. This is what we need. Again, this is not really the address, it's the offset from the image base. So the image base is here, obviously, new address, the same one that we used multiple times. We just need to provide that to RCX. So it's not compiling because this is just a number, a new address is a pointer. So we just go ahead and cast it to ulong64 or something similar to make the compiler happy. And now in order for this to actually be applied, we have to update the context. So we're going to do set thread context here and just pass the context back with our change, which is the updating of RCX there. Okay, so now we're truly kind of done. The last thing we do have to do, of course, is to push the thread into execution. So we just need to resume the thread. So we're going to take the thread and resume it, which now hopefully will do what I would ask it to do. Now, of course, right now we can also close various handles and map stuff. I'm not going to bother with that because the attacker process is going to go away anyway, and that is it. Okay, so first let's build that, see if it builds. It should almost build. So we have some error here with create process. Let's see what the thing is. We have the startup information here. The startup information has probably an A version we need to use. So let's go ahead and do that. And then we have two functions which are not properly linked. So the linker is complaining it doesn't find implementation for them. There's rebase image 64 and anti-query information process. So rebase is coming from image help, but it's not coming from any build normal library we're linking with, normal DLL. We have to use the pragma to add that. So let's do that. So we have image help here. And by the way, if you want to make it even stealthier, you can just use load library and get proc address to get access to this DLL without the actual imports being there within the PE, your attacker PE, so to speak. And then we can do the same thing for anti-DLL, or again, use a load library and get proc address, which is just as good and can make things slightly stealthier. But I'm going to go with the short variation here to keep this video as short as I can. Okay, so now it links, everything is fine. The last thing you need to do is to choose an executable. So let's add a new project here to serve as an executable. I'm going to create a Windows application here. Let's call that injected. Of course, this is not a very good name, but let's use that anyway. So I'm going to have a desktop application here in the sense that I want to have a win main function that doesn't have any dependency on a console or anything like that. So let's create a file called that injected.cpp and quickly create an application. So we have windows.h and what I want to do here is to create our main application. So we have win main that accepts handle to instance, another handle to instance, and we have the command line and the command show, which of course we don't care about any of those. What I'll do is something very simple. I want to call the message box function, and to prove that I am in a different in that particular process, and we might even see something interesting there because the icon might look as the same as the one of the outer process, the one that we're hollowing, so to speak, or at least trying to hollow. So let's get some buffer here we can work with, and then do something like I don't know, WCS print F or something. We can put something into a buffer. So we can say we are injected into PID and provide the process ID here. Get current process ID. something simple. And we have message box just to prove that this is in fact the case and the process will survive. So we have message box, no need to provide anything here. We need to have the text, that's going to be buffer, and the caption is going to be injected, so something, and the type is going to be okay, and maybe little icon for information. And we're done. So this message box is going to be stuck there until we actually, so we have maybe W main here, the linker to be happy. Okay, time to give it a shot. Okay, so one thing we probably want to do, we want to make sure that the injected executable does not depend on anything like changing the code generation here, so it doesn't depend, shouldn't really say anything, but it doesn't depend on the C++ runtime or things like that, but I'm not going to bother with that too much. Let's just open a command window and give it a shot. So here's some terminal opening from Visual Studio. Okay, let's see if it behaves in a nice enough way. Apparently not, it's too big, but anyway, let's go to x64 debug. And you can see here we have our executable that is the attacker, that's hollowish, and we have injected, this is what we want to actually inject. Okay, so let's do that. So hollowish, and I'm going to launch Explorer. I mean, Explorer is very common, so just launch Explorer executable, and I'm going to replace the internals of that executable, of that process really, with injected. So I fear that the rebase image would like a full path. So let's just make it happy. Okay, maybe not that happy. Okay, let's give it again another shot. Sometimes this copy pasting is not working as expected, as we can see right here. So let's do YouTube code, helloish. Sometimes I miss the normal command window, which I'm very soon going to move into. So we have x64, hollowish, right, just can't spell, and debug, and we have injected. Okay, let's see what happens. Okay, do we see anything interesting? Well, nothing seems to show appropriately, which means that we might have some kind of bug. So if this is the case, let's go ahead and debug. What else can we do except debug? Let's debug that, see what happens. These things sometimes happen. Okay, so I'm going to go to the properties and go to debugging and provide the command line. Okay, so Explorer and ddev code x64 debug and then injected.exe. Okay, let's give it a shot. So starting with create process. Is the process created successfully? Yes. So we have an Explorer process here. We can see in process information, what do we have? We have these handles and process ID is F760. Okay, great. Let's create a file for our target file. Does that work? Yes, good. Let's allocate memory. Does that work? It works. Okay, now we're doing the rebasing with that target file. Let's see. Rebasing fails, unfortunately. So something went wrong here. We don't get a new size, the old size. So basically we don't get what we expect. Rebasing is the thing that unfortunately fails. And so the question is, why does it fail? I'm not sure there's ERR here. Actually, there is something. So let's see. Sharing violation. Okay. So maybe I was too quick using here generic read only, and share read. Maybe I need to do share write as well. And that's in fact correct, because re-imaging, the rebasing, actually has to write new information. It has to have the ability to open the file for write access, so I have to allow that. And so yes, I completely agree that this is something I should have done. Okay, let's try it again. It's always fun to try these things. Okay, so here's rebasing. Now it works. Okay, great. We mapping the file. Now opening file mapping for that. Now mapping into memory. Here's our memory. Here's our new address. Of course, they're the same. And then we are parsing the PE, getting the DOS header, getting the NT header, then getting the sections. So we have this information about the sections, quite a bit of sections in the file. In fact, we can check that with total PE if we so desire. Very easy to do. So writing some stuff, writing the header first, we have the image base here and all that. Writing the sections, there's quite a bit of sections. There are 11 sections in this executable. Let's press Ctrl F10 to just do that in one stroke. Let's find the PB. Here's the PB. It's in that process in this address, BBB000. Interesting address. Anyway, we get the context. We calculate the value. You can see all that happening while we're doing these things. Here's RCX, setting thread context, and final step, resuming the thread. Let's hope for the best. So what do we get? Do we get something? So yes, here's my injected process here. You can see the icon is an explorer. So technically the process ID is 44724, and you can see that process ID 44724. Let's just sort by name, it's probably easier. You can see some, here's the one, so that's the Explorer I'm running right now. So there you have it, and we can definitely look at that maybe with some tools like VMMap. This video is going to be long. So here's VMMap. We can choose a process to look at, and we want to look at the 14724. And if we open that up, let me just drag that into this screen. We can see that from an image perspective, we should be able to find Explorer here like normal. It looks like normal Explorer. Nothing seems to be fishy here. Here's Explorer. But in fact, it's running something completely different. And where is that something? It is somewhere in private data. So in private data, we expect to find that something here. Notice the address C20000, the one that we actually use. This is where it's being mapped right now. You can see execute, read, write. Everything here is mapped using this way, which we know it's not ideal, but for this demonstration, it's good enough. Feel free to make it better. So there you have it, process. Well, not exactly hollowing perhaps, but a variation of that. Hopefully you enjoyed that. It was a bit long. I'll see you in the next video.